Have you ever wondered how mathematics and physics are connected? Why does math seem to have all the answers to the mysteries of the universe? The relationship between mathematics and physics is very close. They are like old friends who have lived under the same roof for many years. The laws of physics need mathematics to describe them, such as the famous equation E equals mc squared. Physics problems also require mathematical calculations to solve, such as how often a comet visits Earth. It's like how English is Shakespeare's language, and mathematics is the language of physics. If you don't understand mathematics, reading what physicists write can be a painful experience. Of course, there is also a type of person who doesn't understand mathematics but enjoys discussing physics problems, claiming to have overturned relativity one day and updated the second law of thermodynamics the next. These people are known as Minka in China. From another perspective, physics also makes mathematics more useful. Without physics, mathematics would only design abstract concepts, like imaginary numbers. Physics also inspires mathematicians to explore new mathematical problems, such as group theory, which is an alternative in theoretical physics, and its development has injected many new insights into mathematics. Sometimes, intuition can become an obstacle to understanding the physical world, and that's when we should turn to mathematics for guidance. When we try to understand the strange behavior of quantum particles, mathematics becomes our savior. In these cases, all we can do is follow the math. As long as you get the numbers right, you can trust that mathematics will be closer to reality than your intuition. Intuitively, you might think that quantum particles can't pass through barriers, but if the math says otherwise, then these things can happen. However, things are not always like this. Sometimes, the results predicted by mathematics don't match the theories of physics, and in that case, we cannot just blindly follow the math. For example, if you want to calculate the speed needed to launch an object on a parabolic trajectory, you need to solve a quadratic equation of the form y equals x superscript 2 plus bx plus c. Since this equation contains x superscript 2, you'll get two solutions. One solution is the physical solution, which tells you how to launch the object, while the other is nonsensical, saying your initial speed should be negative, meaning you have to throw the object backward directly into the ground. This solution is mathematically correct but physically meaningless. The reason this happens is because the mathematical model doesn't have the physical constraint, such as the object not being able to pass through the solid ground, or that the launched object could break up in the sky, creating a safety hazard. In most cases, smart physicists can quickly pick the solution they need. They are used to this, and they immediately discard the mathematically valid but physically meaningless result because the universe, as we see it, doesn't work that way. But the statements we've made so far are actually contradictory when you think about it. We first said that when studying physics, you shouldn't trust your intuition, but trust the math, and then we said that when there are two solutions, we should discard the one that doesn't fit our intuition. Isn't that contradictory? This is exactly what we are going to discuss in this chapter. We will talk about complex solutions and how they led people to discover positrons and antimatter. Our story today starts with Paul Dirac. This physicist studied high-speed electrons in quantum mechanics and examined equations related to them. Before Dirac, physicists had already worked out equations for low-speed electrons. In the early 20th century, the revolutionary achievements of quantum mechanics sparked people's imaginations, making them rethink the natural properties of matter at the smallest scale. Quantum mechanics forced physicists to abandon some of their oldest and deepest assumptions. First, that an object can't be in two places at once, and second, that repeating the same experiment should yield the same result. By overturning these classical assumptions, early 20th century physicists completely changed our naive view of the universe, and such changes did not stop at just quantum mechanics. There was also the revolution of relativity, which proved the speed limit of the universe and made people realize that time itself is relative, meaning different people could not agree on the same event. Dirac carefully examined these two crazy mathematical results, which correctly described two incredible theories of physics, and asked himself, what would happen if I combined them? So, he established an equation called the Dirac equation, which described high-speed electrons from both the quantum mechanical and relativistic perspectives. Please remember, these particles are objects in the sense of quantum mechanics. They are not actually small spheres. Sometimes you can think of particles as small spheres, but other times, you need to use the image of quantum waves. Both of these ways of explaining particles have their drawbacks and unreliable situations. When we say that two particles are close enough, these two particles are not actually in contact, and they don't really have surfaces. You can think about it differently by considering their quantum mechanical properties as a superposition. The two particles will disappear and enter a different form of energy, most of the time turning into photons. In this energy, other kinds of particles may also emerge, depending on the size of the energy, which is exactly what happens in the Large Hadron Collider. People make ordinary, common particles collide to produce new types of particles. To some extent, the interactions between particles will ultimately cause the original particles to annihilate and create new ones. Now, particle and antiparticle, as two mirror versions with opposite charges, what's special about their interaction? They attract each other, making it easier for them to collide because their charges are opposite. Moreover, they complement each other perfectly, meaning they will annihilate into a neutral particle, such as a photon. Another thing is that when particles interact, certain quantities are conserved. For example, it was discovered that charge doesn't appear from nowhere and doesn't disappear into nothing. The total charge before and after an interaction remains the same. But why is this the case? We don't know. We don't know what's behind this, we just see this pattern in experiments and incorporate it into our theories. When an electron and its antiparticle, the positron, get close to each other, the opposite charges will pull them closer. Once they collide, the charges will completely cancel out, and the two particles will vanish, with photons emerging. If two electrons get close to each other, their negative charges will repel each other. If you somehow manage to overcome their repulsion, you will get a static negative charge. Charge is conserved before and after collisions, so photons cannot appear in this case. Charge is not the only thing that is conserved. You might wonder if any two particles with equal and opposite charges can annihilate each other. For example, an electron with a -1 charge and a muon with a +1 charge. The answer is no. It seems our universe has another rule, the conservation of electron type and muon type. You cannot use something that is not an electron to annihilate an electron, you can only use the antiparticle of the electron to do so. The same goes for the particles of muons and tau particles. Besides this property, there are many other things that are conserved, such as the number of quarks that make up subatomic particles, which must always be 3 quarks. This conservation is maintained before and after any changes, and this is called the 3-quark rule. All these conservations were discovered by observing particle interactions. By combining these rules, we find that it seems only the collision of particles and antiparticles can result in mutual annihilation. Why are there these strange rules in the universe? We still don't know. Maybe one day we will prove that these rules are just a natural result of deeper particle behaviors. But for now, antiparticles surely hold important clues to the basic laws of the universe. As we've said, antiparticles are the shadow twins of normal particles, and when they collide, they annihilate each other. But we're not done yet, there's something even more interesting. In fact, antiparticles can combine like normal particles to form neutrons and protons. more complex particles and antiparticles. For example, you can combine two anti-down quarks and one anti-up quark to form an antineutron. The resulting antineutron is still electrically neutral, but it is made of antiparticles inside. You can also combine two anti-up quarks and one anti-down quark to form an antiproton, which is similar to a proton except for the negative charge. As we've seen, the mystery of antimatter is deeply intertwined with the fundamental laws of physics. But there are still many questions left unanswered, particularly about the universe's preference for matter over antimatter. Stay tuned, because in the next part of our journey through the cosmos, we'll delve deeper into these unexplained phenomena and the incredible potential of antimatter.